Hello and welcome. Today we're going to be talking about limits of complex functions. And so what we want to do is we want to define what limit z going to z naught f of z is equal to what we'll call w0 means. And determine when it exists for z naught and for a particular function f of z. Okay? So the idea is that, of course, there's not all functions have limits at every value, and but when they do, we want to be able to determine when they do, and also determine what the meaning of this statement means. All right. So let's go back to real variables. And what we know from this is that essentially a limit exists, L, that'll be the value of the limit, when if x going to x naught means f of x gets nearer and nearer to L. Okay, and it gets arbitrarily close. So the idea here is that you have, on the real axis that is, you have some value x naught, and you have some function that may or may not be defined at x naught, but the idea is that if a limit exists, it'll be equal to L, like that. So, and then if I take x going towards it from any direction, left or right, it should be that f of x gets nearer and nearer to L. So we can write that as that x near x naught means f of x is near L. Okay. So of course we've already talked about this notion of nearness. In the complex plane. So we can write that as like, z is near z naught when it's less than some error tolerance. Call that an error tolerance. And we can, because for all limits we're always talking about z or x naught or whatever, z going towards, so we're always talking about z going towards z naught. We're never talking about it actually being there. We always take this to be this. So we're talking about the deleted neighborhood of z naught with a radius of delta, right? Because that's what that is right here, right? Okay, so we want to that's our definition of nearness for z. We want to know what happens in the other plane. So let's get a new sheet of paper. Okay, so we have this notion of an error tolerance. In z, okay? All right, so the idea then is we want to know, we have to also define nearness in, or nearness of f of z to w, our candidate limit for our function, okay? So we can do that. So the idea then is that what we want to state basically is z near z naught means f of z is near W naught. All right, so let's see if we can be as precise as possible. So what we're going to define nearness of f of z to 0 as setting there's some neighborhood. We'll call it epsilon is a tolerance, such that f of z minus w naught is less than epsilon. So that's nearness in the w plane. So now let's put this together. What we're going to do is set epsilon to greater than 0 to be arbitrary tolerance. A limit exists if for every epsilon we pick, there exists a delta such that any z in the deleted neighborhood around z naught means that f of z for those z's in this deleted neighborhood, so that's dn z naught comma delta, means f of z is within the specified error tolerance of our limit. So what this means is, another way of writing this is f of that deleted neighborhood is inside the neighborhood w naught epsilon. So that would be another way of writing it, right? And that's the idea here, and I'll kind of draw out the picture. If we have, there is our z naught, and then I'm going to put that deleted neighborhood around it. And if I were to take this function and map it in, and here is our specified, here's our w naught, there's our epsilon, that this function would completely be inside of that epsilon there. Okay, so this is in the w plane, and here is the z plane. Okay, so that's the idea, and that's a very, very precise definition of a limit. So there's other alternative ways of stating the same thing. You're basically saying that f of z goes towards w naught for every path in z plane every path in the z plane z going to z naught. Okay, so that's the idea that, and this is more similar to what you've talked about maybe in Calc 3, is if we have z, we have some path going in towards z. No matter which path you take, it has to be that that f of z is going towards or getting very near w naught. So if I take a path coming in that way or that way, they all work. But all of those conditions are covered if we consider our neighborhood idea. So that's the idea. So let's do a simple example of what we're talking about here. So let's talk about this example of a function f of z is equal to I z over 2. Okay, and I want to take the limit z going to 1 in the complex plane of f of z. And I want to know what that limit is. And so, for instance, I could actually just put z equals 1 in here. So f of 1 is equal to I over 2. So that would be my candidate limit. I want to know if the function itself will approach I over 2 as from any path. Okay, so the question is it equal to I over 2? So that's our candidate limit. So let's try to do this analysis. So in general, right, we always start with setting an epsilon. So we want to say that we have some epsilon. It's an arbitrary value. And we want that our function is near that value. We want to see the function if it's near our candidate value for our limit. So what we can do is then see, so this is our statement. I want to know what values of z always create this situation. Can I find a deleted neighborhood of z's that will always have this function nearby I over 2? So let's put it in. Let's substitute in our definition. That's going to be I over 2 z minus I over 2. And I'm going to do a little algebra here now. We can see that I can factor out an I over 2. Okay. And going further, we can now take the complex modulus and break it up. Okay, so and then we see that the complex modulus of I over 2 is actually just 1/2. And that's z minus 1. All right, so the idea is, can we find a neighborhood, a deleted neighborhood around 1 of a certain delta that guarantees it for whatever? Can I find this value? Can I find this set? And it's clear that what we have here, if I write this down again, so we have this here, that epsilon is less than 1/2 z minus 1. Well, I can rewrite that as 2 epsilon is greater than z minus 1. Okay, so clearly if I set, so what if I do if I set delta is equal to 2 epsilon, so I can pick an epsilon and I can always find a delta. That's our goal, is every time I have an epsilon, I can always find a delta that will work. So what I can do is then say that the set then is going to be z where according to this formula here that we have 2 epsilon is equal to delta is less than z minus 1. And I just have to set that greater than 0 to make it a deleted neighborhood. And that's my set that will always guarantee that that the function is very near I over 2. So any arbitrary error tolerance, I can guarantee that error tolerance by setting delta equal to 2 epsilon. And that this set, so this makes that the function deleted neighborhood of 1, 2 epsilon is always going to be inside the function. It's always going to be inside the neighborhood epsilon. I over 2, comma epsilon. All right, so that's one example. Let's go try an example where things are a bit more complicated. So now let's try the function f of z is equal to, and it's going to be a piecewise definition. It's going to be z for x greater than 0, greater than or equal to 0, and 0 for x less than 0. All right, so what this, and of course we're talking about z being equal to x plus I y. So on the complex plane, what we have out here, everything out here, all of that is all 0. That point always gets mapped to the 0 point. And here, this point here always gets mapped to itself. So here, it's just, the value here is always z. So what I want to know is the limit z going to 0 of f of z. Well, okay, I don't know if this limit exists or what it is, but I can guess. And I want to guess and see if I can confirm my guess. All right? So of course, f of 0 is going to be equal to 0. Okay, because I plug it in. So x equals 0. That gives me over here, and I plug in z equals 0, and I get 0 out. Okay, so I want to know if I get close to that. All right, so again, I'm going to start as before, epsilon. I want to find my function f of z minus 0. Okay, so that's just going to be f of z. Okay, all right, so I want to find out if I can, so really this has to be broken down into two cases. So we'll talk about case 1, and that's going to be the x is less than 0 case. And then we can see that epsilon greater than, and what we have inside of here then is always going to be 0, right? For every x less than 0, it's always that. And this is always guaranteed. So for every value, so if I want to find a neighborhood around my point 0, anything on this side, it doesn't really, I have no restriction on delta because I can make delta to be anything. So if z minus 0, it could be anything. And it doesn't matter because it's all getting mapped to 0. So I'm out here, I get mapped to 0. So no matter what I am, where I am on this side of the z-plane, I always go to 0. So I always be arbitrarily close to my candidate limit. All right. So no restriction on delta. But now let's try case 2, x greater than or equal to 0. Then we get epsilon is greater than z minus 0 is greater than z. All right, so now of course we require that delta then has to be what we want for the neighborhood, the deleted neighborhood around 0 for delta has to be. All right, but we see already from this point here that means I can take, these two are equivalent statements, so I can take delta to be equal to epsilon, and that works. Okay, so now for every epsilon I can find a delta. Okay, great. And that means that the limit as z approaches 0 of f of z is equal to 0 exists and is a true statement. Okay, so now let's try a further example. Now let's try the same function. Oops. Z for x is greater than or equal to 0, and 0 for x less than 0. Now I'm going to try the limit as z goes to I of f of z. So first of all, what candidate limit do we have? Well, first of all, we can tell immediately, here's my I value. Now if I come in from this side, the function value, f from any z, and I'll say any z where x is less than 0, the value is 0. So that could be one candidate. I'll put a question mark there. But that's not in the domain, so if I actually evaluate f at I, it's equal to I. So another candidate would be I. All right, so clearly there's a mismatch between these two things. So we can see here that clearly the limit does not exist. Because I can find two different paths. If I take a path this way versus a path that way, they clearly don't agree. And therefore, because I is not equal to 0, the limit doesn't exist. Okay, so we could be done there, but let's just try to maybe just go over this a little bit more rigorously. We'll actually do a little example of picking epsilon is equal to 1.1. Okay, let's see if we can find out what's happening here. So I've actually picked a particular value of epsilon, and I'm going to say my candidate limit is is w is equal to I. I'm going to see if that could be the limit. So of course 1.1 is less than f of z minus I, right? And so again I have to work on those two cases. So the case is x less than 0, I have a 0 minus I, and that's the same thing as I, which is equal to 1. So that's clearly less than 1.1, so we're okay. All right? That seems to work. We can find anything on So if I'm looking at my complex plane, here's my I value. Anything in this neighborhood I can pick for any delta value. It's completely unrestricted again. So again, no restriction on delta, right? That seems to work, provided I have epsilon 1.1. All right, and now I'll go to the other side. 1.1 less than z, so this is the half of the problem there, z minus I. And clearly, if I take delta to be equal to epsilon, again, we're okay. Because any value on this side, within this range will always be, if I take delta is equal to epsilon, we're going to be okay. All right, so now let's see if we can break this. Now set delta is equal to 0.1. Or sorry, nope, oops. I mean epsilon is equal to 0.1. All right, so this is because it has to work for every value of epsilon. Now I'm going to try this particular value. Okay. All right. So then what I'm going to do is go through those cases again. So case 1, which is x less than 0, I can write. So we write it as epsilon is equal to 0.1, and we know that the function has to be within this error tolerance. So I write f of z minus I, right? Our candidate limit. And we see that this is, but on this case here, for this case, f of z is equal to 0 minus I, which is equal to the absolute, the magnitude of I, which is equal to 1. So we obtain a problem here because 0.1 is definitely, this is not true. So our procedure of picking epsilon equal 0.1 leads to a violation or a contradiction. So we conclude that the limit does not exist because we found a particular epsilon value that does not guarantee f of z is near the limit omega naught equals I. All right. So we found an error tolerance there's no way we could actually achieve. That would be a better way of saying it. All right, so hopefully that gives you some insight into limits and a few examples of how to do it. But again, we always start with this, epsilon less than f of z minus omega naught. And then we do some sort of analysis to determine if we can find a delta equal to something there that will always guarantee this statement. And that's always how it works. That's always how we go through that procedure. Okay, so this is a very technical, very proofy section. I think it's important to go through this a little bit because I think it's the essence of science what we're doing here. We're really applying an error tolerance and then seeing if we can satisfy that error tolerance with a certain input tolerance. So we apply an error tolerance and then we find an input tolerance that will guarantee it. And that idea, I think, is very sensible to try to understand in any kind of context involving science or engineering. So thank you very much.